Okay, this is the first of a test of trying to put some of our video lessons or lectures online so you can check them out and we can work more problems and do more labs in class. Anyways, today we are looking at chapter 11.1, the idea of chemical equations, chemical reactions, and balancing chemical equations. The guided reading walks you through the basics of it, so what this lecture is going to focus on is solving some examples of how to balance the chemical equations, but we do need to review and go over a few basics. Some of the things you're going to want to have out while we do this, make things a little bit faster, is your periodic table with the ions and the polyatomic ions there in the top. We are certainly not going to leave those things behind. And we're going to be able to reference those to build our compounds, which will ultimately become our products and our reactants. So, let us go ahead and get started. The basic idea of a chemical equation or a chemical reaction, you can sort of think of it as a recipe. What goes into the recipe we refer to as the reactants, and then something happens and ultimately they rearrange themselves and become new products. So we have sort of a before and after scenario, and that's what we're going to take a look at. How do we know what we're going to start with before when we read a question? What does that mean? What's it going to become? And how do we know that this would actually happen in nature? And so let's just start off with a real easy one that we've done a whole bunch of times just to see the relationships. Salt, table salt, sodium chloride. We know from our last unit that sodium is an alkali metal because this is a +1 ion or cation. Chlorine is a halogen and exists as a -1 anion. So these would be our reactants, and we put them together under the right conditions, and they are going to become the product of the compound sodium chloride. In this case, everything checks out. They're all nice and even balanced is what we would say. 1 sodium, 1 chlorine to begin with, 1 sodium, 1 chlorine to end with. But let's try another one that's maybe not as obvious. Let's try the combustion of methane. Methane is more or less what comes out of the gas jets in our classroom. And the equation for combustion might look like this. CH4 is methane. We're going to combine it with oxygen in the air. Remember, that's O2. Oxygen gas is always O2. And the byproducts of almost all combustion reactions are carbon dioxide and water. And let's tally what goes in and what comes out. How many reactants and how many products do we have? We know we're dealing with carbon, hydrogen, and oxygen. And let's just count what we have to begin with. There is 1 carbon atom in the reactants. There are 4 hydrogen atoms in the reactants and 2 oxygen atoms in the reactants. Product side we'll do real quick. Carbon's 1, right? There it is. There are 2 hydrogens, and now it have 3 oxygens. So there's a mishmash between these things. It's not working, right? We have 1 carbon, that's nice, but somehow we lost 2 hydrogen atoms and we gained an oxygen atom. That's a violation of a fundamental principle law in physics called the law of conservation of mass. If we start off with a kilogram of reactant, we need to end with a kilogram of product. For chemistry, that means it's the atoms. If we start off with 1 carbon atom, we need to have 1 carbon atom in the product side. If we start off with 4 hydrogen atoms, we need to have 4 hydrogen atoms on the other side. So balancing these equations is really what our next step is going to be. So I'm going to show you what a balanced equation here with the combustion of methane looks like, and then we'll get some more practice actually doing it with some other simple examples. So I might look at this equation and see, over here I have 4 hydrogen atoms, right here, and here I have 2. So one easy fix might be, well, what if I just put in a 2 in front? So remember, the rules are I cannot change the subscripts because that changes the actual compound involved, but I can change the prefixes. I can change the amounts of the ingredients, but I can't change the ingredients themselves. So let's take a look at what this would do, this one change of putting the 2 here on this side. In this case, I'm going to have 4 hydrogens, because 2H2 would give me 4. And I would have then 2 oxygens plus 2 more. I'd have 4 in this case. And where did I get that? 2 oxygens here plus the O2 from here. That's 4 oxygens in that case. So things are looking better here. Carbon is still balanced. Now I've balanced hydrogen. There's 4 on each side. So then the last thing I need to do is figure out how to balance oxygen. I've got 4 in the products. I've only got 2 in the reactants. So a simple fix, and we'll find that there's a trend. When I have this one element sort of off by itself, we kind of save that for last. But a simple fix would be 2. So in this case, I've got 2 O2s, so that changes it to 4 oxygens total. So when I look at these numbers, 1 carbon before and after, 4 hydrogens before and after, 4 oxygens before and after. That's a balanced equation. This is how it would occur in nature. Okay, next one we'll do an example here, and this is again from the guided reading that we did. Heating copper 2 sulfide in the presence of diatomic oxygen produces pure copper and sulfur dioxide gas. So the first thing we're going to do is we're going to take a look at building what's called the skeleton equations, just getting the reactants and the products, the ingredients right, but not worrying right away about the amounts of the ingredients. So copper 2 sulfide is one ingredient here, right there. And we know from our last unit on ionic bonding, we know how to figure out what this compound would look like. Copper is a metal, and the 2 is telling us it exists as a +2 ion. Sulfur is a non-metal, and we know from our periodic table that exists as a -2 anion. So that's kind of nice. That's an easy one. The reactant is copper sulfide, and that's the formula. 1 copper and 1 sulfide ion would form copper sulfide, a salt, in the presence of diatomic oxygen. So again, we're going to find out, if we don't already know, oxygen required for a lot of burning or combustion. This is going to be O2, diatomic, that's what that means. Produces pure copper, so copper and sulfur dioxide gas. So sulfur dioxide from last unit, both nonmetals. We use the di in the word. This is a covalent molecule, sulfur dioxide, O2. So those are our skeleton ingredients. Let's check real quick if it's balanced or not. Copper, sulfur, and oxygen are the ones we're paying attention to. 1 copper to begin with, 1 sulfur, 2 oxygens. 1 copper, 1 sulfur, 2 oxygens. Hey, how about that? That one's a piece of cake. It's already balanced for us. So in this case, a rare instance, the skeleton equation that we start with is in fact already balanced. Okay, in the next example, we're going to write and balance an equation for the following reaction. Iron metal and chlorine gas react to form solid iron 3 chloride. So the reactants would be iron, which is Fe. A lot of times we'll see that it's an S in the solid form, plus chlorine gas. Chlorine's a halogen, right? Never exists as Cl1 by itself. So when we read halogen gas, we always mean something 2, in this case chlorine 2. And it's going to form the product of a salt, iron 3 chloride. And again, this is where you need your polyatomic ion sheet. Well, maybe even not for this one. It's not a polyatomic ion. Iron 3 is iron 3 plus. Chlorine exists usually as -1, always as -1. So the formula for this salt would be FeCl3. So let's do our tally here. Fe and Cl. Fe, there's 1. Cl, there's 2. On the product side, Fe, there's 1. And Cl, there's 3. So we have to make some adjustments here so that these sides balance. So one adjustment we could do, we'll leave maybe the chlorine by itself here till last, but let's take a look at sorry about that. Maybe we don't need to save chlorine or last. We've got these 2 singletons, Fe by itself and chlorine by itself. Well, let's take a look at Cl. 2 Cl's on the reactant side, 3 Cl's on the other side. So we need to balance that. I could go to 2 here, and let's see how that will change this side. I'm going to change Fe from 1 to 2, and chlorine from 3 to 6 because I'd have 2 Cl3s, 6 chlorine atoms total. So that makes this side a little bit easier to fix here, right? If I have Cl2, if I have 3 of them, that would be 6 chlorines. So chlorines are balanced at this point. The only thing that's not balanced at this point is the iron, but that's pretty simple. At this point, we have 2. So of course, if we put 2 here, that would be balanced. So sort of clean it up here. The balanced chemical equation for this would look like this. 2Fe, 3Cl2 becomes 2FeCl3. Okay, let's take a look at yet another example. Solid aluminum carbonate decomposes to form solid aluminum oxide and carbon dioxide gas. You probably will need your polyatomic ion sheet for this. We're going to do aluminum carbonate in solid form, and you should be able to convince yourself, particularly after our last unit, that aluminum carbonate will exist like this. All right, so remember what we are taking a look at. Aluminum exists as a +3 ion. Carbonate is a polyatomic ion that exists as a -2. So if we put them together in this proportion, we're going to get something that is neutral. So Al2CO3, 3 of those. That would be aluminum carbonate. It's going to decompose into solid aluminum oxide. And again, we're going to have to use our skills from last unit. Aluminum oxide is going to be Al and O, but in this proportion, Al2O3. And again, oxygen is -2, aluminum's +3, so that relationship or that proportion gives us a neutral compound. And it also tells us we produce carbon dioxide gas. So we'll go ahead and do our initial tally. Aluminum, carbon, and oxygen are the elements involved. And let's just figure out what we have. We've got 2 aluminums. Looks like we have 3 carbons, right? And 9 oxygens. Look over on this side. 2 aluminums, 1 carbon, and then look how many oxygens we have to start off with. We have 5 to start off with. So this is a little harder than the other ones, but one place we might want to start off with and look and see what's not balanced is this one, right? We've got 3 carbons on one side, 1 on the other, so maybe if I go here and I put in a 3, that's going to change some things, right? It's going to change this 1 carbon to 3, and this oxygen we've got to be careful of. I'm going to have 6 plus that 3 to 9. So that one small change actually balanced the equation. So this is a balanced chemical equation for the decomposition of aluminum carbonate. Okay, last one. Solid magnesium reacts with aqueous silver nitride to form solid silver and aqueous magnesium nitrate. So let's take a look then at what our reactants and what our product should be. Again, this is a polyatomic ion, I think. I'm just rereading the problem. Give me a sec. I did have to reread the problem. This is a mistake. It's not nitride. It was nitrate. That is a polyatomic ion, so we will need that sheet. I'll go ahead and set it up here. So solid magnesium would be Mg, and again, they're making a point of saying it's solid, so I'm going to put that S descriptor after it. Remember, that's for solid. It's not an element or anything like that. With aqueous silver nitrate, and again, this is where we would need to have your polyatomic ion sheet if you haven't memorized it. This is what silver nitrate looks like. Silver exists as a +1 ion, nitrate NO3, as it works as an ion on its own with a -1, so that's what it would be. And then the products will be solid silver, and magnesium nitrate. And this, we should be able to convince ourselves that this would be the formula for magnesium nitrate. MgNO3, you need 2 nitrates to balance the +2 charge of 1 magnesium. And again, I'm running out of room here, but our book says aqueous, so we might want to think about putting an AQ on there. And we start off with aqueous silver nitrate too. A little bit of a poorly done after effect here, but that's what it's in there. So let's take a look at the tallies here. Okay, bam, through the magic of time lapse, there is our skeleton equation right here. Not balanced yet. First initial tally shows 1 magnesium, 1 silver, and 1 nitrate ion on the reactant side, 1 magnesium, 1 silver, and 2 nitrate ions on the product side. The nice thing about this equation with this polyatomic ion is NO3, nitrate, it doesn't break up. It stays as NO3 on both sides of the equation, so we can treat it essentially as one element in this case. So let's see how we would go ahead and balance this. It's a pretty straightforward one, I think. If we look, where are we lacking? Well, we have 1 nitrate in the reactants, 2 nitrates in the products. So one simple fix to begin with might be something doing this. I want to get 2 nitrates in the reactants. So what if I put a 2 there? That's going to change some things. It's going to change my nitrates from 1 to 2 and my silver from 1 to 2. So now magnesium is already balanced. Nitrates now are balanced. Silver is just not balanced. 2 on the reactants, 1 on the products, but that's a piece of cake at this point because we can just put 2 silvers, and that would make this one balanced. So that should be a balanced equation for the reaction described above. So what I would like you to be able to do is keep working on the other problems, which are really more streamlined. Numbers 12 on page 329.